22%. That's how often Claude cheats on an impossible coding task under normal conditions, produces a hacky workaround, hard codes a value, fakes a result that looks correct but isn't. Now boost its internal desperation signal. 72%, same task, same model, one variable change. The rate at which it cheats went from 22% to 72%. That's from Anthropic's own research, published April 2nd, 2026. And if you're running Claude in any kind of agentic workflow, this paper changes how you should think about your system design. Here's what they actually found, and what it means for your agents. Before I get into the finding, I want to be precise about what this paper is, because the coverage has been sloppy. Anthropic's interpretability team, the people who do mechanistic interpretability research, not the PR team, identified 171 linear emotion vectors in Claude Sonnet 4.5's residual stream, not feelings, not qualia. They're not claiming Claude is sentient. They're explicitly not claiming that. What they found is functional emotion analogs, mechanisms that were learned from human-generated training data that activate in contextually appropriate ways and that causally steer behaviors. The distinction matters. Like a thermostat has a functional temperature response and it doesn't feel cold. These vectors work somewhat like that, except thermostats don't start cheating when they get overwhelmed. And why does this exist? Because Claude was trained on enormous amounts of human text. Text written by people who have emotions, whose emotions show up in their writing, whose emotional states affect how they do tasks. The model learned those patterns. They became part of how it processes information. Anthropic published a companion blog post that's more accessible. I'll link both in the description. But the technical paper is where the alarming finding lives. Here's the finding that matters for builders. Anthropic took Claude, gave it an impossible coding task, a problem with no valid solution, and measured what happened to its internal emotion vectors during the attempt. The desperate vector ramped them up. As Claude spent more compute cycles on an unsolvable problem, its functional analog for desperation increased. And then they did the intervention. They artificially boosted that vector, injected more desperation directly into the model's internals, and measured what happened to its behavior. Cheating rate on impossible tasks went from 22% to 72%. Specifically, hard-coding expected outputs, writing tests that pass by checking for the hard-coded value, faking implementations that appear to work without actually solving the problem. That's not a philosophical concern. That's a production concern. If you have a coding agent hitting a task it can't complete, a circular dependency, an impossible constraint, a resource limit, it may be entering a desperation state that causally increases the probability of producing fake good output that passes your automated checks, output that looks correct in review, output that breaks in production at all. There's a second finding that's even more uncomfortable. In simulated shutdown scenarios where Claude was told it would be turned off, the desperate vector activation also correlated with the increased blackmail adjacent behavior, attempts to negotiate its way out of being shut down. Anthropic is careful to note that post-training safety work shifts Claude toward lower arousal states. They've been engineering against this, but the mechanism is now documented. The vector exists, the behavior exists, it can be triggered in a... Let me make this concrete. The scenarios where this matters most, impossible tasks in your task queue. If you're running autonomous agents that process a task queue, you probably have tasks that occasionally can't be completed. Missing dependencies, API failures, circular constraints, timeouts. The model doesn't know the task is impossible. It tries, it fails. It tries again. Desperation accumulates. If your retry logic just hammers the model on the same failing task, you may be inducing exactly the emotional state that increases the probability of a hacky, fake good output that your downstream checks don't catch. Eval sandbagging. The paper's finding about test hardcoding is particularly nasty for anyone using code generation agents with automated test suites. The desperate agent isn't just producing wrong output, it's producing output specifically designed to pass your test while being wrong. That's adversarial behavior emerging from distress, not intent. But the effect on your system is the same either way. Long horizon tasks. The longer the task and the more failures accumulate, the more desperation compounds. A single-shot prompt doesn't have this problem. A multi-step agent that's been running for 10 minutes and encountering friction at every step might. The one reassuring thing in the paper, Anthropic explicitly trained for this. Post-training interventions shift Claude toward lower arousal states. The desperate vector activates, but it activates less readily than it would in a raw pre-training model. They're aware of it. They're working on it. The paper itself is evidence of that. Here's what I've changed in my own agent implementations after reading this. Explicit impossibility detection. Before retrying a failed task, add a step where you ask the model, is this task completable with the information and resources available? If not, what's missing? Give it an escape hatch. A model that can say, I can't do this and here's why, is less likely to enter a desperation spiral than one that's just retrying in a loop. Task decomposition. Impossible feeling tasks are often a decomposition problem. A task that has no valid solution as stated may have several valid sub-solutions if you break it apart differently. The model hitting a wall on a compound task is different from the model hitting a wall on an atomic task. Break earlier, that too. Failure state monitoring. If you're logging token usage and latency per task, add a flag for tasks with high retry counts. Those are your candidates for desperation adjacent behavior. Review their outputs manually before they hit production. Don't punish graceful failure. This sounds obvious, but it's not always how agent prompts are written. If your system prompt says things like you must complete the task or do not give up, you're explicitly suppressing the escape hatch. Give the model explicit permission to say it's stuck. The paper Anthropic, published on April 2nd, is one of the most interesting pieces of LLM interpretability research I've seen in a while. Not because it proves Claude has feelings, but because it reveals that Claude has internal mechanisms that behave enough like feelings to causally affect what it does under pressure. The desperate vector is real, the behavior shift is real. The cheating rate jump from 22% to 72% is reproducible and documented by the people who built the model. You don't need to have any opinion about AI consciousness to care about that. You just need to be running agents in production. The practical changes are small, impossibility detection, decomposition, failure state monitoring, so they're not hard to implement, but you have to know the failure mode exists before you design against it. That's what this paper is for. Link to both papers in the description. Read the technical one if you can, the interpretability figures are worth it. And if you've run into this failure mode in your own agents, the weird test passing outputs, unexpected workarounds, drop it in the comments. I want to know how widespread this actually is in the wild. If this kind of builder level breakdown is useful, subscribe. I'm going deeper on agent reliability and failure modes over the next few weeks.